Okay, we are going to continue on here to chapter 4, and this will be the first chapter will be on the second exam. Obviously, it's not on the exam that's coming up on Thursday. Not Thursday, that would be a wrong day. How about Wednesday? Sounds good. And you'll be taking that, I think, during lab time. All right, so in this chapter, we're going to talk about obviously what it says elements, atoms, and ions. We're mainly going to talk about at the beginning here some experiments that led to our understanding of the atom. We then will talk about, I think, some things like atomic number, mass number, how to figure out how many protons, electrons, and neutrons an atom has. And then we will get into the periodic table and I kind of finish up talking a little bit about ions, I think, at the end. So a lot of information packed into here. So the first thing we're going to kind of talk about is formulas. And when we talk about formulas, when we write something, for example, like our H2O, which is our water, we do use obviously the chemical symbols to do so. We also use a subscript to indicate how many atoms of those guys we have. The subscript here always goes to the guy to the left. So that would indicate in this case of water that we do have 2 hydrogen atoms. If there is nothing written, much like a lot of chemistry, if there's nothing written, it still goes to the guy to the left, but it does mean 1. So typically speaking, we don't write the ones down or anything like that when we just have 1 of something in chemistry. So obviously in the case of water here, we would have 1 oxygen in the middle, for example, and 2 hydrogen atoms there on the ends. Now, when we talk about a formula, we talk about sort of a compound in general. Let's just remind ourselves of some differences in some terminology. An element is really the basic sort of building blocks of everything. You can think of elements kind of like the alphabet. There's only like, say, 26 letters, I think, still. But different combinations of those letters will give you different words. And same idea here with elements, different combinations of elements will give you different compounds along the way. Now, a compound and a molecule are oftentimes kind of confused, or if there's a difference between them. A molecule is basically 2 or more atoms together. And an atom is the basic representation of any element, as we'll talk about today as well. Obviously, it has protons, electrons, and neutrons in it. Now, when we talk about a molecule, again, it could be 2 of the same, 2 or more of the same element. It could be 2 or more of different elements. Those are all molecules. When we talk about elements, they actually can be what are referred to as being monoatomic, which essentially means that they come as one. So most things that are elements that you see on the periodic table, they come monoatomic, which means they do come naturally uncombined as ones. They also have elements that are diatomic molecules. And diatomic molecules means that it's basically 2 atoms together. Things like hydrogen, nitrogen, oxygen, chlorine, fluorine, bromine, and iodine here. They all basically come as 2s, and that's how they naturally come if they're uncombined. So we have like hydrogen, we have oxygen, a couple of oxygen atoms, and so forth. Now, each of these things here are elements, and they're also molecules because they meet the definition of a molecule, which is just simply you got 2 or more atoms together. That is different than a compound. A compound, again, is 2 or more atoms of different elements. So in order for it to be a compound, you do need that additional sort of restriction, which means that there is at least 2 or more different elements involved. So like our water example a second ago there, that has obviously hydrogen and oxygen involved, which means water is a compound. Water is also a molecule because it definitely has 3 atoms together. So that's 2 or more atoms. So it is a molecule. It's also a compound. It is not an element because it contains both the element hydrogen and oxygen together. And like I said before, these guys over here are both molecules and elements, but they are not compounds because they only contain the same element involved. Any questions on that there? Now, when we look at a compound, thank you. It has the same relative number of atoms of each element. So whenever you have water, no matter where you get the water from, it will always have this combination. It'll have 2 hydrogens for every 1 oxygen involved. A chemical formula basically expresses the type of atoms present, and the number indicates by that subscript that is present. And again, it goes to the guy to the left in that particular case. When we write our formulas, we do follow certain rules, and typically we do use the chemical symbols as we've been talking about. And really, the chemical symbols come one of 2 ways. They either come as a 1-letter sort of symbol or a 2-letter symbol. And if it's a 1-letter symbol, we do just use the capital letter for it. So if it's just a 1-letter symbol, we use those capitals. If it is a 2-letter symbol, we always capitalize the first letter and lowercase the second. So always capital the first, lowercase the second. And that's really important when you're writing formulas, for example, is if you capitalize everything and you write CO like that versus CO like that, CO, capital C, capital O is actually carbon monoxide. And that's very different than obviously capital C, lowercase o, which is cobalt, which is an element. So you want to make sure that if you're somebody that writes capital letters for everything, that you don't do that when you're writing chemical formulas. Otherwise, you might actually be writing something that you're not intending to do so. Once again, here, this is carbon dioxide, nothing written. So that's 1 carbon, 2 oxygen atoms, 1 nitrogen atom, and 3 hydrogen atoms in NH3 in that particular case. So those tell us how many atoms there are later on, as we'll talk about in a later chapter as well. They also represent what are known as the moles of each of those elements as well. And we'll see that, those little subscripts a little bit later on in a different chapter. All right, so why don't you take a moment here for each of these sort of examples. Why don't you write the proper formula based on the description that you got? Okay, so let's take a look. So first one, we got 6 carbon atoms. So symbol for carbon is C, and 6 would go bottom right of it. And it also has 6 hydrogen atoms, so hydrogen and a 6 there. So a little C6H6 action. Next one, we have half as many calcium. So calcium, capital C, lowercase a. And chlorine, which is Cl. So we have twice as many, or half the number of calcium. So if I make calcium, I make chlorine 2, half of 2 is 1, so I would have something like CaCl2 would be our formula in this case. And lastly here, we have equal numbers of sodium, which is Na, and nitrogen, which is N, and 3 times the amount of oxygens, which would be O3, so a little sodium nitrate, calcium chloride. Now you may be asking, is there other formulas you could get for these two? Technically speaking, yes and no. Yes in the context of this question, but no in the sense, as we will learn in later chapter as well, that are even at the end of this chapter, I think, when you put like a metal and non-metal together, which is what these two guys are, you want to put them together in the simplest way that will give them 0 with their charges. And, for example, if you have Ca2Cl4, that is half the number of atoms. But you could reduce each of these guys down by 2, which gets us back to, what we had there. So whenever you kind of put a metal and non-metal together, you always want to put them, as we will talk about later on in this chapter as well, in the simplest whole number ratio, basically, that will give you really an overall charge of 0 in that particular case. Any questions on any of those there? All right, so now we're going to talk about really some of these experiments in the atom and some of the experiments that led to our understanding of the atom and where we find different parts of the atom. And as we go through this, I'll sort of mention, obviously the things that you should know for sure, and some of the stuff, that maybe you don't need to know too much about, but we'll talk about what you do need to know. So let's talk about this, and really a lot of it began back in really old times with the idea by philosophers that all matter is basically composed of these very small, indivisible, indestructible sort of particles, which they called atomos, which basically led to obviously atoms that we call today, meaning basically uncuttable and you can't really break it apart. Now, a lot of what was sort of thought about in terms of matter as they were studying this early on in the 18th century was this idea that most things were either pure substances. And again, that is something that is just by itself, like you have a pure substance of just iron metal or a pure substance of water, whatever it may be. Remember, when we mix a couple of pure substances together or more than two, we can make mixtures of those things. We have the law of composition, which means regardless of where you get something, it always has really the same composition by mass. So for example, if we take our water, which is our H2O, hydrogen is basically 1 gram, and oxygen is basically 16 grams. So we basically have 2 hydrogens, which is about 2. So we take about 16 divided by 2, that's 8 grams. So basically for every gram of hydrogen, we have about 8 grams of oxygen that's present. No matter, again, where you get your water from, they all have basically that same sort of proportion or ratio. Now, one of the first sort of ideas about sort of the atom was brought to us by Dalton and his atomic theory. And Dalton was an interesting guy. He used to like to write the weather down every day of his life. He never married. He did obviously go bowling on Thursdays, which is obviously important information and probably will show up on all exams except for the first one. So make sure you say Thursday, not like Saturday or Friday or any of those type of things. But really, besides going bowling on Thursdays, he did like to come up with an idea or a theory about atoms, which you do need to know the different parts of it. Now, as we talked about in terms of theories, theories are not always 100% correct. Remember that further work can sort of maybe validate or invalidate some parts of a theory, and Dalton's is no different. There are a couple of main sort of ideas that came out of Dalton's atomic theory that later on were sort of proven to be sort of incorrect, and we'll talk about those couple of things in just a second. But these are some of the main aspects of Dalton's atomic theory. He said that elements are composed of these extremely small particles that are called atoms. Sort of the idea from Dalton, and kind of before, was this idea that atoms are indestructible, and really nuclear reactions sort of disproves that sort of idea. You could definitely change one atom into something else through some type of nuclear reaction. Chemical reactions, as we'll talk about, that doesn't happen, but it does in sort of nuclear reactions. So that is one of the sort of ideas that, is not so correct. The next sort of point also is one of the ideas that is not so correct anymore as well. And that's the idea that all atoms of a given element are identical. They have the same size, the same mass, and the same chemical properties. Now, when Dalton did it, they didn't know of the existence of what we'll talk a little bit about, and we'll talk a lot more about when you take 1b, which are isotopes. And isotopes are basically the same element, but they have different masses, which means obviously they're not identical. If you have 2 isotopes that are the same element, but they have different masses, as we'll talk about, really the different mass is a result of having different numbers of neutrons, for example, but they are still the same element. So the existence of isotopes sort of disproved that part of Dalton's atomic theory, that every element or atom of every element is identical to each other. Atoms of one element are different than atoms of another, so that is good still. So obviously if you had an atom of carbon, it is different than an atom of iron. It has different masses, protons, neutrons, and so forth. Compounds are composed of atoms of more than one element, as we've been talking about. And in a chemical reaction, really the only thing that occurs is breaking of bonds and making of bonds, like we talked about there in chapter 10 when we were talking about energy. It does not result in any creation of anything or destruction of anything. And that's sort of the law of conservation of mass. We don't create nor destroy anything in a chemical reaction. Matter is not created nor destroyed. Again, in a nuclear reaction, you do get different things produced. That's why when we look at an equation, for example, if we had something that has 6 carbons in it on the left, we will end with 6 carbons on the right-hand side of the equation when it's all done, or the reaction. Those carbons will just be in different things on the product side, but we will still have the same number of carbons that we started with. We'll have the same number of hydrogens if we have hydrogens or any elements. That's why we balance equations when we use them, because we don't lose elements along the way. They just get rearranged through breaking and making new bonds. And that also means conservation of mass is the idea that carbon is 12 grams over here, and all 12 or 6 of those carbons on the right will be 12 grams each. That means you have the exact same mass of carbon on each side of the equation. So you'll have the same mass of carbon you started with and ended with. And that's what the idea of the law of conservation of mass. So you do need to know Dalton's atomic theory. You do need to know, again, the couple of points that are not so correct. Again, atoms not indestructible, and the existence of isotopes means that atoms of the same element are not identical to each other as well. Any questions on that there? So another sort of idea of Dalton was this idea of law of multiple proportions. And the idea there is he saw basically compounds as rearrangements of different elements sort of together. So in this case, these all contain nitrogen and oxygen, but different sort of proportions of these elements that come together will give these guys different sort of properties and give us different compounds. But one sort of relationship that you see sort of in all these is if you take a look at sort of the mass to mass relationship or ratio of each of these things, we have sort of a relationship of a whole number of multiples. So what I mean by that is nitrogen is about 1401 grams, oxygen is about 16 grams. So if you want to know the grams of oxygen or the ratio of oxygen to nitrogen in this compound, we could take 16 divided by 1401. And if you do that on your calculator there, you will get 1.14. Now, if we go to the NO2 to the right there, that is 2 oxygens, each at 16, and nitrogen at 1401. So if we again do our oxygen to nitrogen sort of ratio, we would have 32 grams divided by 1401 grams. And if we take 32 divided by 1401, we get 2.28 in terms of our ratio. If I take 2.28, which is this ratio of nitrogen to oxygen atoms, and this ratio of oxygen and nitrogen atom basically, and divide them, that gives us the whole number of 2, or multiple of 2. You can even do it for the guy on the bottom. That is 1401 for that nitrogen, 1401 for that nitrogen, and 16 for that guy. So if we take the oxygen to nitrogen, 16 grams divided by 28.02, and if I take 16 divided by 28.02, I get this number here, 0.571. And if I take this ratio, for example, 1.14 divided by 0.571, I also get a ratio of about 2, basically. So again, that idea there is these elements will come together always in sort of whole number ratios when they come together, regardless if there's different combinations of the same elements. If you take the one element to the other ratio, you'll always get they come together in this sort of whole number ratio. That is why when we put formulas together, for example, we don't have like a half atom of oxygen or a half of atom of nitrogen. We either get a whole number of each of these things. Any questions on that there? Yeah. It really doesn't matter as long as you compare the same ones on top and the same one on the bottom. So we wouldn't want to do like nitrogen, oxygen one, and then oxygen, nitrogen over on the other one. So on this one, I did oxygen on top for all of them and nitrogen on the bottom for all of them. And that would be how you kind of get the same ratio. That way, when you compare them, one ratio to the other, you're comparing kind of apples to apples, not kind of the reverse of it. So, other questions? All right. So we're now going to talk about some experiments that helped us understand sort of the structure of the atom. And one of the things that really helps us in chemistry and helped us understand sort of the nature of the atom was basically using a very simple concept in chemistry, which is an important concept. It is the idea of opposites attract, sometimes called electrostatic attraction. And basically what that means in chemistry, much like in life, positive and negative thing are sort of attracted to each other. They will attract one another. You have positive and positive, they will repel one another and not want to be near each other. And if you have something that's negative and negative, they also will repel each other, right? Just like if you have two positive people together, that's a lot of positivity, right, in one room. So they don't want to be near each other. You have two negative people, a lot of negativity in one room, same deal, right? So they always say you go and find something that balances you out, right? So you find positive and negative, kind of nice, happy medium. So that's a really important concept, is that electrostatic attraction. When you have a positive thing and a negative thing, they will be attracted to each other. And things that have the same type of charge, typically in chemistry, want to be as far away as possible from one another. And this is really important since when we talk about the atom, there are protons, electrons, and neutrons, as we'll talk about, which they do have charges. So a lot of these experiments use sort of this idea of opposites attract to help them sort of probe atoms. And they use a few important radioactive sort of particles. They use alpha particles, for example, and that's abbreviated with the little alpha symbol. Those are positively charged radioactive particles. They are essentially, as again you'll learn in 1B, they are essentially helium, basically, is what it is. It's basically the helium nucleus. There are beta particles, which has the symbol kind of like a B, and that is a negatively charged radioactive particle. And the last sort of radioactive sort of particles that was used a lot is gamma rays. And this has a little symbol that kind of looks like that. And these actually have no charge. So these are kind of like neutral type of radioactivity. They're super high in energy. You definitely don't want to be around something that's a gamma emitter for a long period of time without the proper protection, for example. Now, this idea of opposites attract and using some of these radioactive sort of particles is really important when we think about an atom that has particles that do have charges. So they're able to sort of explore sort of what is going on with those sort of charged particles within the atom. They also can use things like an electrical field and a magnetic field to do so. So an electrical field, for example, has a positive side and a negative side to it. And if you had an electrical field and you shot a particle at it and it kind of bent upwards towards the positive side of that electrical field, that would tell you that that particle most likely had what type of charge? Yeah, it would most likely have a negative charge, right? Because it's going to be attracted to the positive side of the electrical field. Same thing if you shot that thing and it kind of bent towards the negative side, that would probably tell you that that particle most likely had a positive sort of charge. And if you shot something and it went straight-ish type drawn line and wasn't really affected by either of those electrical fields, that would give you kind of a no charge situation on that particular one. A magnetic field works kind of the same way. You have kind of a north pole, south pole, and kind of does a similar sort of way the beam would bend towards either north or south, depending on the charge of it. So a lot of experiments use these sort of radioactive sort of particles to help them explore the atom. And let's take a look at some of that. So based on Dalton's atomic theory, the atom, as we talked about, is basically the basic unit that can come into chemical combination. Although the atom is extremely small, it still actually contains an internal structure that's even smaller, and they contain what are referred to as subatomic particles. And there's three types of subatomic particles that you might be familiar with, and those are our friends, the electrons, which are negatively charged, the protons, which are positively charged, and we have neutrons, which have no charge. So although the atom is extremely small, we have these even smaller particles that basically make them up. And there were several experiments done that sort of helped us understand, again, some of the nature of the electron, proton, and neutrons, and where they may be found within the atom. So let's talk about first really the electron. So when we look at the electron, one of the biggest sort of experiments are sort of increased understanding of the electron came about with what is referred to as the CRT, which is a cathode ray tube. And a cathode ray tube is a setup such as this, for example. It has a sort of an electrical field sort of side, or really more of a negative plate and a positive plate. And this is really negatively charged particles like electrons, which would be moving away from the negative side towards the positive side of the sort of tube. Now, usually sometimes what they'll do is put some type of material there at the end of the tube where the beam of electrons are heading towards that will sort of fluoresce as it hits it. And you can actually see sort of where that beam is sort of going. You might be familiar maybe with CRT if you've seen a really old TV, nothing like what we have these days that hang flat on a wall, but really big TVs. Maybe grandparents or somebody's got some of those laying around on the floor. Used to call the TV repairmen out. They open up the back of the repair of the TV and repair it. You know, just didn't go to like Costco and grab another one in the back of the truck, right? So they actually would repair it. And inside there's actually the picture tube, which is basically a CRT cathode ray tube. Maybe you've seen an older computer monitor that has like the big back coming out of it, not the flat screen, obviously, but it has like a really big back. Those are CRT monitors that also has you know, a CRT sort of in it. So these were used a lot to explore really the nature of the electron. And as I mentioned before, basically what you have is that negatively charged particles, which goes basically towards the positive side, which is known as the anode, and away from the cathode, which is known as the negative side of that arrangement. And as I said, it will hit kind of the glass, and you'll be able to kind of see where it's at. And here, as you can see, as we talked about there, North Pole, South Pole, this would be more of a magnetic field. This is our electrical field. And again, having those also in play sometimes can affect charge type particles like electrons or protons and neutrons. They obviously would not affect. And that's what we see here. Our guy tilting towards the positive, more negative in North Pole. Guy heading down there towards the positive side, going to be more negative towards the South Pole as well. Let's take a look at a cathode ray tube and a classic one here.
This is a cathode ray or Crookes tube. It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So again, you can see obviously the magnet or magnetic field has an effect on that beam, as it is a charged sort of beam there, negatively charged particles. So you can obviously play around with the beam there and move it around. So the person that sort of did a lot of work with a cathode ray tube was J.J. Thomson. And that's him right there in his cathode ray tube down there, I think. And basically, what he found was an important sort of aspect in terms of electrons. Using those, he was able to calculate the charge to mass of an electron. So he was able to calculate basically the ratio of charge to mass for an electron. And that's actually this number down here, negative 1.76 times 10 to the 8. C is a coulomb. A coulomb is a unit of electrical charge, and G is grams, which is a mass. So that is charge to mass, basically, there. And this was a nice big step forward in terms of sort of understanding electrons by calculating this sort of charge to mass of an electron. Sort of a really sort of complementary type of experiment that was done in terms of electrons was really the next one we're going to talk about, which is Millikan. And Millikan did what is referred to as the oil drop experiment. And basically what he did was he had this chamber and he shot oil droplets into the chamber here and he atomized it by heating it up. And basically what would happen was there's a kind of a magnetic field, I'm sorry, electrical field here, positive, negative, and the little droplet of oil would go through the little hole, and as it would fall, it actually would gain a charge from friction and gravity. And what he was able to do in this experiment was essentially adjust the electrical field within his chamber to a point where essentially the oil droplet just kind of hung there. So it didn't fall, it didn't go up. He was able to kind of dial in really the charge to kind of lock the oil droplet into place, as you can kind of see here, maybe, if it plays. There you go. So there goes the oil droplets. It's going to start to fall, pick up a charge, adjusting the electrical field will kind of suspend the oil droplet there. And again, what that allowed Millikan to do through the oil drop experiment was to basically figure out the charge of an electron. And the charge of an electron that he figured out was negative 1.6 times 10 to the negative 19 coulombs. The reason why these two experiments are really important, if you take them together, if you take Millikan, who figured out the charge of an electron, and you combine it with Thomson's experiment where he figured out the charge to mass of an electron, and you divide basically the charge by the charge to mass, charge will cancel, and from those two experiments, the mass of an electron can basically be found from those two numbers. Basically, you take the charge divided by the charge to mass, and that will tell you basically what the mass of an electron is. So you do need to know Thomson worked with the CRT tubes and came out of that experiment was the charge to mass of an electron. You need to know that Millikan sort of followed it up with the oil drop experiment, a little bit about the experiment, and the main thing that came out of that, which is the charge on an electron. And using both of those experiments together, as we just talked about, the mass of an electron can be determined. And the mass of an electron, which is a number that really does sort of pop up a lot in chemistry, 9.09 times 10 to the minus 28 grams. Sometimes you'll see it in kilograms very commonly kind of given to you, so you could do the kilogram conversion on it. But that's a number that you probably should know. Sometimes people use 9.11 as well instead of the 9.09, so it's somewhere in that ballpark most people will sort of use. And again, that's something like 9.09 times 10 to the minus 31 kilograms that you sometimes see as well. So that is a really large number or small number? That is like a super small number, right? You're going to go 28 places to the left and add a bunch of zeros, right? Going to make that a really, really small number. So the mass here of an electron is relatively small. And again, that's an important sort of number we'll talk about here in just a second. So at this point, based on what has happened by the early 1900s, there was a couple of features of the atom that was sort of known. They known from these previous experiments that we just talked about that they contain electrons, which obviously are negatively charged. The other thing that they knew was that the atom was electrically neutral, which means if they do for sure contain negatively charged electrons, they must also contain something that is positively charged, right? So they have to have something that is positively charged to balance it out so that it is neutral. And around the turn of the last century, the accepted model of the atom was one done by Thomson, actually a slightly different Thomson. And that is what is referred to as the plum pudding model. And essentially in that model, the atom was thought to be a sphere. And within that sphere, all the positive charge was basically just spread out and diffused basically over that sphere. And within that sort of positive charge spread out there that we have, they had electrons that were embedded inside. So they had these electrons embedded within it. And the idea there is plum pudding is kind of like a rice pudding sort of dessert, and it has raisins in it. So the idea of the raisins are like the electrons. The pudding is kind of like the positive charge that's really, really spread out. And the other really major feature of the plum pudding model was they felt that in this model, most of the mass of the atom was the electrons. So they felt at this point that we have this kind of smear of positive charge spread out. We have these electrons kind of embedded in there, and pretty much the electrons are going to be most of the mass of the atom. You definitely need to know the plum pudding model and sort of the aspects of it. Any questions on that there? Now, with this being sort of the accepted model of the atom, further experiments were done. And really the next sort of major experiment along the way that helped us get a much better understanding of the atom was one that was done by Rutherford. And this is a much prettier picture, obviously, of our plum pudding. Again, the blue is all the positive. The red circles there are embedded electrons. Now, Rutherford did, along with a couple other guys, what is referred to as the gold foil experiment. And the gold foil experiment is a really important experiment, and it really did sort of shape our modern idea of what the atom looks like, what is going on with the atom. So the idea of what happened with Rutherford in his experiment is he took these alpha particles, again, those are our positively charged particles, and what he essentially did was shoot them at pieces of metal like gold foil and some other metals as well. And they observed basically what happened. And what they observed happen was really quite different than what they thought was going to happen. So based off the previous model there, which is our plum pudding model, what they anticipated happening in this case was if they took these alpha particles, which are positively charged particles, relatively heavy, they're moving pretty fast, they expected that these guys would punch through that positively charged kind of pudding and be a little bit deflected as it went through there. So if you thought about, for example, my paper here is the atom, and all the positive charge is spread out over this entire piece of paper. And for example, I held one side, somebody else held the other side super tight, right? And we shot like a pen or something at it really fast, right? It probably would be able to bounce through, punch through it, and then as it would pop out the other side, right, it would be a little bit of deflection as it would pop out sort of the other side of the paper. And that's essentially what they really thought was going to happen when they did this experiment. They were really surprised, though, when they did the experiment that what they saw was pretty much no problem. Most of those alpha particles kind of sail through undeflected. So those alpha particles kind of sail through pretty much undeflected. They did see, though, that every so often they would see an alpha particle be scattered at a really large angle. It might even come back to basically the source where it was shot out of in this case. So if we try to think about, what's going on in this case and what this is actually telling us, it's important to think about what each of those sort of results mean that they saw. First off, if they shot these alpha particles and it just sailed through no problem, what did it hit? Did it hit anything? It probably didn't. So if you take my pen example, if I throw my pen with nothing in front of it, it's not going to have a problem. It's just going to keep sailing, right? It's not going to alter course or anything like that. And that means it obviously didn't hit anything, most of those particles. But in order to make those heavy, fast-moving, positively charged alpha particles bounce off at these really large angles, it did have to hit something, right? And it probably had to hit something that had what type of charge? It has to hit something that had a positive charge, right? Because that would repel it. If it hit something that was negatively charged, it would just stick, right? It would be really happy at that point, right? Because it would want to stay there. So what happens in this case is it had to hit something that was really, really densely positive to make those fast-moving, positively charged alpha particles to bounce off at those really large angles. So if you think about sort of the idea of the model of the atom they were dealing with, which was their positive charge in that plum pudding model was spread out pretty diffused over the entire thing, right? Not really densely concentrated. So the idea here is perhaps the positive charge is not really spread out all over my paper, but if I took my paper, right, and I folded it however many times you fold it, right? They say 7 times and then you're done pretty much or something like that. And I take all my positive charge instead, right, and fold it all the way down like this. And if I try to shoot a pen through it, it's definitely going to hit it and bounce off, right? Because all the positive charge now is basically concealed in a very, very small sort of area. And what that ultimately meant was they really did, based on the plum pudding model, have to kind of go back now and sort of revisit the model of the atom. Any questions on that there? So let's take a look at that there.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So as you can see here in this diagram of that, what we saw is most of them just kind of sailed right through, but definitely those ones that hit the nucleus basically, or that positively charged area, definitely scattered at a really, really large angle. So this was really important in terms of its findings. They were really surprised on that. They again thought that most of them should have no problem bouncing through that kind of pudding of positive charge to spread out. They compared it again to sort of like shooting a gun at a piece of paper and having it come back at you. Not good. And again, on the left is what they thought would happen. On the right is more so what happened. Again, we're getting these large sort of deflection. So what this basically meant was we do have to kind of revisit our plum pudding model that they had going into this experiment and basically say not so correct, right? So models, theories, not always correct, can be later proven to be not so correct. And they had to basically propose sort of a new model for the atom and really the modern model of the atom that we deal with. And basically what they said was that the atom was mostly empty space. And again, that's what accounts for all those alpha particles not having any issues, just kind of sailing right through. It also contains a very dense positive core, which was called the nucleus. And later experiments, as we'll talk about, shows that's where we find our protons, which are positive. And then like in 1936, that is when neutrons were also found there as well that have no charge. And the next really major sort of difference between the plum pudding model and really the current model is most of the mass of the atom is the nucleus. So the nucleus, not the electrons, actually make up most of the mass of the atom. So essentially what we got going on is we have this really dense positive core, this nucleus that has protons that are positively charged, has neutrons which have no charge in the nucleus. And outside the nucleus, we have the electrons really flying around that empty space, sometimes referred to as the electron cloud. As we will talk about, as you might know, electrons actually travel pretty randomly. They don't travel in pretty circles or anything like that around the nucleus. They are traveling pretty randomly. As we'll talk about in a later chapter, there's something known as the Heisenberg uncertainty principle, which basically says that particles like electrons, the more you know about how it's traveling, the less you know about its position, and vice versa. Basically, the more you know about its position, the less you know how it is basically traveling. One thing that we do know, though, is electrons are negatively charged, right? And overall, the nucleus is positively charged. Is there an attraction between those two things? There is, right? That's the opposite attraction. So the electrons, which are negatively charged flying around the nucleus, they are attracted to the nucleus, which is ultimately positively charged. That's why all your electrons just don't leave, right? And they just don't fly away. They have like almost like a rope sort of attachment to it. Some tighter than others, which is why some electrons are involved in bonding and some are not involved in bonding, depending on their location. The strength of opposite attraction there, electrostatic attraction, positive and negative things, does increase with overall charge. So the greater, say, the positive and negative charge, it will be held tighter than a lower positive and negative charge. So if you're comparing, say, a +1 and a -1 in terms of strength, will be attracted to each other, but they will be less attracted to each other, or I guess the +3 and -3 would be a much stronger attraction than what you would see in the +1, -1. They both would be attracted to each other. And again, that's why we have two different types of electrons that we'll talk about. Valence electrons, which are involved in bonding, and core electrons, which are really close to the nucleus, not involved at all in bonding. So this table here is obviously some of the summaries of the experiments we just talked about. You do need to know, obviously, the plum pudding model, like I said. You do need to know sort of Rutherford's experiment, what he did, what he thought would happen, and what actually happened, and obviously what the current model of the atom is, and comparison to the plum pudding model. Yeah. Any questions on any of that there? Okay. Now, that means that as we've been talking about, protons were sort of discovered there in the nucleus, and they are positively charged. And experiments have shown that basically the mass of a proton is 1.67252 times 10 to the minus 24. If you remember, our electron is something like 9.09 times 10 to the minus 28 grams, right? So the electron is significantly less massive than a proton. A proton is much more heavier, and it's about 1,800 or so times heavier than any electron moving around. A reminder that when you look at negative exponents there in scientific notation, the smaller negative exponent is actually the larger number, right? Because the bottom guy, you're going 24 places and adding zeros. The top guy, you're going 28 places and adding zeros, which makes it a lot smaller. This also sort of lends credit to the idea that no, it's not the electrons that are the most massive part of the atom, but it's actually the nucleus is the most massive part of the atom, because in the nucleus we have protons, which is each proton is 1,800 or so times heavier than any electron that's flying around. So that does make sense in terms of it being the nucleus that is basically most of the mass of the atom. So at this point, we can think of the nucleus as having most of the mass of the atom, but occupies a very small volume of it. So I guess it's relatable. That's where they had the Super Bowl, right? So you can think of the atom as the size of the Superdome there, and like the nucleus is like a small marble on the 50-yard line, right in the middle of the place. So a very small volume, but is the most massive part of the atom, mostly empty space, right? If you ever been to the Superdome, you feel like you're falling out of the seats when you're sitting. It's very, very steep and stuff. Even if you're sitting on your seats, you're like, I'm going to fall. So protons are confined to the nucleus. Again, electrons are out some distance from the nucleus, moving around in a random sort of motion. That leaves us this idea that was an idea for a really long time, that a lot of people believed, hey, in addition to protons, there is some other particle that's probably in the nucleus as well. And it wasn't really until the 1930s there that a guy by the name of Chadwick did a bunch of experiments where he noticed a lot of particles coming off that really resembled gamma rays. And if you remember, gamma rays basically are neutral sort of radioactive particles. And that is sort of what he saw coming off of these experiments he did with different pieces of metal. It would be sort of emitting these type of things. And he called those guys neutrons. And neutrons were thought of as being also in the nucleus. And it has a mass of 1.67495 times 10 to the minus 24. That number goes out to that many digits because if you compare it to the number we just saw for the proton, it actually beats the proton if you go out that many digits. So in terms of those three subatomic particles, it is actually the neutron that is the heaviest, followed really close by the proton, and way below them, about 1,800 times less heavy, is the electron. It is the lightest of those three particles. I would say for our class, maybe has to know the exact numbers of those. I would probably invest some time into probably the electron. It does pop up as your chemistry career goes. But you do need to know between a neutron, proton, and electron, which one is the most heaviest and least heaviest and stuff like that. And obviously their location. So once again, we have in our nucleus, our protons, which are positive, our neutrons, which have no charge. And again, out in that empty space, sometimes referred to as electron density, we have our electrons basically moving around. Any questions on that there? There's our comparison. As you can see, just barely, our neutron does beat out our proton. So here's sort of a diagram of that. And as you can see, the nucleus is relatively small, but most massive. And this sort of shows up a little bit on the screen there a little bit. But there's actually different layers of pink as you kind of move out there, or red as you move from the center out. And this is what's sometimes referred to as the electron density map. And basically what that means is that's sort of that empty space where those electrons are flying around in. And when you see a darker area, that usually means, I'm not really sure where the electron is at any particular point, but there's a pretty good probability that you could find an electron in that area. And obviously, as you can see, as you sort of fan out to the edges, it gets less red. So there's still a probability that you could find an electron out there, but probably a lower probability than, say, closer in by the nucleus. And that does make sense. Again, by the nucleus, which is ultimately positively charged, we're going to get a lot of positive negative attraction happening in that area. Again, we do not know exactly where the electron is or how it's moving, but there is just, again, a probability. That's really what we talk about. And when we get into the chapter 11, I think when we talk about electrons, electron configuration, that's really what we talk about when we talk about electrons and how they're moving is a high probability of finding an electron in a particular location within the atom. Again, not really sure how it's got there, how it's moving, or where it currently is located. Any questions on that there? All right, so again, those experiments we talked about, you need to know about the experiments, what came out of those experiments. Any questions on any of that there? Okay. So most of the chemistry of a atom comes from electrons. And if you just think about sort of the diagram of what we were just looking at, clearly we have our nucleus, and if you have two atoms, you basically have your electrons on the outside moving around. So clearly those are the first two things that would come in contact with each other. As atoms come near each other, those electrons which are on the outside would obviously interact with one another. When we have chemical reactions, which is pretty much all we talk about in this particular class, the only thing involved are those electrons. So when we talked about earlier in chapter 10, that's what's happening in a reaction is we're breaking bonds and making bonds. That is all electrons. So it has nothing to do with anything happening in the nucleus. It is all just those electrons. As we will talk about here shortly, it is those particles that are actually in the nucleus that's most important for pretty much making that atom a certain element or not a certain element, depending on how many protons you have, for example. That is really the important thing. So in normal chemical reactions, we don't touch the nucleus. And that is why when we balance an equation, if we started like my example earlier, that we had 6 carbons on the left-hand side of the arrow, we should still end up with 6 carbons on the right-hand side of the arrow because we didn't really change any elements because we didn't touch anything in the nucleus. And nuclear reactions, that is totally different. That's all you do is change the stuff in the nucleus so you get different elements and form. So let's talk about some other properties of atoms: the atomic number, mass number, and isotopes. The atomic number, which is sometimes abbreviated with a Z to represent atomic number, the definition of the atomic number is the number of protons there are in an atom of an element. Now, that is the actual definition, which is the number of protons there are. And since we know protons are positively charged, that would mean that if we are dealing with some type of neutral atom, the only thing that is negative in an atom are electrons, right? So we got protons that are positive, we got electrons that are negative, and we have neutrons that have no charge. So if we know the atomic number, which is number of protons, and the thing has no charge, that would mean that we would have an equal number of electrons. So if you're dealing with a neutral atom and you know the atomic number are the number of protons, which is essentially the same thing, that essentially will tell you how many electrons you have. It's really important, though, if you're asked just a straight up question of give me the definition of what an atomic number is, the definition of atomic number is only the number of protons. So that is the actual definition of it. It has nothing to do with electrons. So if you say it is the number of protons and electrons, you would be incorrect. So if you're asked that question, what is the atomic number definition? It is only the protons. But if you're dealing with a neutral atom, the side note to that is it will tell you how many electrons there are. Where can you find the atomic number? Well, right up there on the periodic table. That would be the number right up on top. So the number up on top of the symbol on the periodic table is the atomic number. If you look at the periodic table there on the wall and you look at all the numbers that come above it, do any of the numbers repeat? They do not. They're all different numbers. That means that every single element has its own atomic number and also has its own number of protons. So right off of the bat from that conversation, if you were asked the question of protons, electrons, and neutrons, which one would be the most important in terms of what element you're dealing with? It actually would be the protons, right? So every single element up there has a different number of protons, which means if I'm dealing with hydrogen, I know it has 1 proton. I can never have a hydrogen that has 7 protons because the one that has 7 protons up there is, number 7 is nitrogen, yeah? So number 7 is nitrogen. So nitrogen and a neutral nitrogen atom would have, as it says on the bottom there, 7 protons, which are positively charged. And if it is neutral, it would also have 7 electrons, which are negatively charged. 7 positives, 7 negatives equals 0, no charge. How do I know it has no charge when I write it? I don't see anything written there, yeah? So if it did have a charge, that is where it would be written. In the case of nitrogen, it would say something like -3 there or something like that, or 3 minus. But if you do not see anything there, or if you're talking about a neutral nitrogen atom, again, the protons and electrons need to equal each other to basically equal 0 to give you no charge. Neutrons doesn't matter in terms of charge because neutrons have no charge, so they can't affect it, right? So the protons are the most important because if you change the protons, then you change what element it is. And that's why everybody has its own unique atomic number, which also means that if you know the protons are the atomic number, which once again is basically the same thing, all you need is a periodic table and you'll know exactly what element you're dealing with, right? Or if you know what element you're dealing with, all you need is a periodic table and you can find out how many protons it has and its atomic number. So very important piece of information that is up there. Every element has, like I said, its own atomic number. Another really important sort of number that we come across is the mass number. And the mass number is sometimes abbreviated with an A. And the mass number, different than the atomic number, is the number of protons and the number of neutrons there are in an atom. So the mass number tells you both protons and neutrons. And why that number is important along with the atomic number is if you take the mass number, which is our number of protons plus our number of neutrons, and you take the atomic number we were just talking about a second ago, which is our number of protons, and if you simply just subtract those two numbers, protons will cancel, and that will tell you the number of neutrons. So if you want to figure out how many neutrons there are in a particular atom, if you know the mass number and you know the atomic number, you can basically just subtract the two, and it will tell you how many how many neutrons there are in that particular element. When you calculate those things, the mass number, the atomic number, the number of protons, electrons, and neutrons, they all have to be pretty much positive whole numbers. So they all should be positive whole numbers. That brings up the next question, which is, when I go to my friend, the periodic table, which I like, and I see another number. I know this top number here is the atomic number. Is this bottom number the mass number? What do you think? Is the bottom number the mass number? Bottom number is not the mass number. It is the atomic mass, actually. Why do I know that is not the mass number? Because the last thing I just said there, that box on the bottom, those numbers need to be what type of numbers? They all need to be pretty much whole numbers, right? And if you look at the periodic table, pretty much every single number that's on the bottom of all the symbols, they're decimals. There's very few kind of whole numbers. So you can only find the atomic number on the periodic table, which is the number up on top, which is obviously the number of protons. The mass number is not found on the periodic table. What confuses a lot of people and what a lot of people think is this: a lot of times the mass number and the atomic number that you see up there, which is based off of how many protons, electrons, and neutrons you have, they're actually very close numbers. So sometimes people think, oh, they must have just rounded maybe the number you see on the periodic table there on the bottom, and that's not the case. So do not be the person on the exam when we have these questions that starts writing decimals for the mass number, because you will get an X. Yes, you don't want that. So the way to remember it has to be whole numbers. So how could you figure out the neutrons, the mass numbers? In these type of problems, you will be given enough information basically to figure that out, how many neutrons you have, how many protons are the mass number based on the question that you're given. You'll be able to definitely figure it out. So once again, only the atomic number can be found up there on the periodic table. Mass number is not on the periodic table. And again, all those things do need to be whole numbers: protons, electrons, neutrons. You can't have a half an electron or, a quarter of a proton. And again, mass numbers and atomic numbers do need to be, whole numbers as well. Any questions on that? All right, I think actually we're going to lay it up right there. It's good stopping.